All right. And here are our responses. Okay. Yeah, these are our responses. All right. I think they look okay to me. Almost, maybe. I don't know. I don't know. Let's see. Okay. So I need to do it myself. I cannot I don't memorize the answers. You shouldn't do it either. Okay. So the first question is you're given the pHs of milk of magnesia, a solution of milk of magnesia, and your stomach. All right. So let's leave the stomach first. Okay. So you have the pH to be 2.0. Therefore, we know. So pH is, let me write that one more time. pH is negative log H3O plus concentration. So if you're asked to find H3O plus concentration, H3O plus concentration should be equal to, right, this relationship over here. So H3O plus concentration is 10 to the power of negative pH. That's it. You're done. Okay. So that would be 10 to the power of pH is minus 2. So it should be negative 2 here, molar. That's it. Done. That's the H2O plus concentration in your stomach. Okay. And then for milk of magnesia, you do the same thing. So for milk of magnesia, okay, I'll do it on this side. H3O plus concentration should be, okay, 10 to the power of negative pH. What is the pH here? 10.5. So negative 10.5 molar. And this is going to be something 10 to the power of minus 11. So you can plug this into the calculator and it should give you a number. What is that number? Anybody? What did you get? Come back. Something, okay? 3.2? Yeah, so I'll go with that, okay? It's 3.2. Chandni, what was the typo again? Oh, in the answers? Oh, should be negative. This should be the H3 plus concentration in milk of magnesia. All right, I'll come back to the type in a second, okay? And I think I also asked you to find the OH minus concentration in milk of magnesia. So how do we do that? We know there are two ways of doing it. I'll do my least favorite method first. I'm sorry, less favorite method. Anyway, first, and then I'll do my favorite method after that, okay? So we know H3O plus concentration times OH minus concentration. By the way, I'm going to include questions like this on tomorrow's quiz. How about that? It's so easy, okay? This is all you use. All right, you know this is equal to 10 to the power of minus 14. Okay, H3O plus concentration is 10 to the power of minus 10.5. Okay, times OH minus is, let me write that. I don't usually do this, but I'll do this anyway. It's equal to 10 to the power of minus 14. Okay, therefore, OH minus concentration must be, okay, 10 to the power of minus 14 divided by 10 to the power of minus 10.5, which is 10 to the power of negative 3.5. Yeah, 3.5. 3.5 molar. That's it. That's the OH minus concentration in milk of magnesia. And then the POH, okay? POH is negative log OH minus concentration. Okay, so that should be equal to negative log 10 to the power of minus 3.5, which is 3.5. Pretty straightforward, right? That's it. I think that's all the questions we have there, right? Yeah. That's same as in the power of negative 3.5. Yeah. Uh-huh. So if you put this in calculator, yeah, 10 to the power of negative 3.5 is 3 point something negative 10 to the power of negative 4. It's the same thing, right? So this is just, working with the log scale here. All right. What questions, concerns, comments do we have about this? Anything? Any questions, concerns, comments? Yes, I have a question, Aiden. Thank you. And I have the microphone there. What's the name, Miss? One more time. Name first.
I was just gonna
What's
ask,
your name, Miss?
oh, Isa.
Isa, go ahead.
Yeah. Should it
Please
have,
pay attention.
is it supposed to have a unit of moles?
Molar.
all-
For concentration units are molar. Uppercase M.
Right? Okay. I was just making sure.
Yeah, yeah. Uh-huh.
Okay, thank you.
Yeah. Any other questions, concerns, comments? So pH, POH, or anything to the any P does not have any units, but the concentration has units of molar. Uppercase M. All right. Any other questions, concerns, comments? If we have a question like this on the test, can we do it? If not, I mean, what is still bothering you? How can we fix it? How can I fix it? Anything? Any? Okay. Okay. Yeah, these are pretty straightforward calculations. Okay. I mean, just going back and forth. The only thing is you need to have the relationship correct. That's it. Okay. And what's the relationship? One more time, if I can. As my okay. All right, I can do it. Okay. So the most important thing over here is this relationship over here. Okay, that's it. All right. We'll practice a little bit more a little bit later, but for now, I'm going to clear my doodling. And then -2, -4, -11. I think Chandri, they look okay, right? Oh, so I don't think H3O plus concentration is correct here. Oh no, it is fine. It is fine, I think. Okay. All right. So no, yeah, it is not. 10 to the power of -3.5, right? No, this is wrong. So this should be 10 to the power of -10.5. Papa is wrong here. This is not correct. Right? Yeah. So any questions about that? So top pad is wrong there. We already did the calculation. All right. Yes. Andrea? What? Huh? Yeah. So now I'm going, I will fix that later. But it should be 10 should be molar. Okay. All right. Now with that, I'm going to clear my doodling one more time. I want to move on to this. Okay. So just to remind us about what we have done so far, okay? We talked about the most important reaction in this unit, which is this. Okay. This is the most important reaction in this unit, the autoionization of water. Okay. And then we build this relationship, derive these relationships as well. And then what we talked about was adding certain things to water changes it H3O plus concentration. Okay. So, and those certain things can be acids or bases. Okay. If we add an acid, if I can find my pen, a second. Okay, this is what we have discussed so far. So acids work like this. So let me write the generic form of acid like HA. When you add an acid to water, liquid, okay, it's going to donate a proton to water. Acids donate protons. So if you should have that definition somewhere in your notes. Not because I'm going to ask you to define what an acid is, but you should know what an acid, okay? Acids donate water to donate protons to water. And as a result of that, I'm going to get protonated water. So by the way, so maybe I should have mentioned this the other day as well. I kept saying proton. What is a proton? Proton is an H plus ion. Why do I call that and get a proton? Because if you think about it, hydrogen has only one proton and one electron. If you remove that one electron, you are left with what? Just one proton. Okay, that's why we call H plus protons. Anyway, just a side story. Anyway, so that gives us protonated water or hydronium ions, plus this will have a negative charge now because HA bond breaks towards A. As a result of that, we are going to get an A minus ion. Okay, and that's how the acids react with water. Okay, and then what we can do is while we are at this, you can see that we have an equilibrium here, right? If you have an equilibrium, what can I write next? Yeah, so if you have an equilibrium, what can I write next? For an equilibrium, I can write, thank you, equilibrium constant expression, right? So I'm going to say K for this is equal to H3O plus concentration times A minus concentration. These are my products, divided by HA concentration. Okay. And because I'm talking about acid dissociating, okay, I'm going to call this K sub A. Why? Because this is acid dissociation. All right. What questions, concerns, comments do we have about this? Anything? You know what? While we are at this, I'll do the base as well. Then we'll have some fun, okay? So when it comes to bases, maybe I should define. So acids donate proton, donate H plus, right? Then when it comes to bases, okay, when it comes to bases, okay, they accept protons. Accept protons, okay? So let's think about how a base would react. So bases come with lone pairs, okay? Because those lone pairs are important to accept protons from water. So here's a base, B. I'm going to indicate as it has a B. When that reacts with water, okay, what it does is it's going to grab a proton from water. As a result of that, this neutral B is going to have an H attached to it and a positive charge. Okay, if it was neutral to begin with, then it's going to have a positive charge because it grabbed a proton from water. This is aqueous. Plus, we are going to have OH minus ions. OH minus AQ. Okay, so we can define the equilibrium constant for this as well. K is equal to BH plus concentration times OH minus concentration divided by concentration of B. I'm not going to include water because water is in the liquid phase. That concentration do not change. Okay, and because we are talking about base dissociation, we call this K sub B. Yeah. And while we're at this, I mean, we can, if you want to do this, we can do it like this as well. We can define what we call pKa for this. pKa would be negative log Ka. On your whiteboards, what is pKb then? Go ahead. If pKa is negative log Ka, pKb must be, thank you, negative log Kb. Negative log Kb. We are just, these are just for bookkeeping purposes, you know. All right. What questions, concerns, comments do we have about this? Anything? Any questions, concerns, comments? All right. So let's have some fun. Now, we know what acids are and bases are now. What we want to do is, we want to think about what makes acids so bases strong. What do you mean by strong and weak? Okay. So to do that, I'm going to use this question. I'm pretty sure we can figure it out and then we'll discuss. Here we go. Here are some acids. I want you to arrange them from weakest at the top. All right, I think we have close to 90% answers now. Meaning I'm going to close this question in 5, 4, 3, 2, and 1. Okay, so let's see how we did. Here, our response. This is the most popular response. Most of us said HCl is the strongest acid, okay, with the highest Ka value. And on the other hand, acetic acid is the weakest acid out of the acids given here. Why? It has the lowest Ka value, right? And that's the correct response as well. Only 1/3 of the class got there. Maybe we swap them. If not, we need to make this small note in our one-page note or in our notes. Let me do it in my notebook. Okay. So the note should go like this. Strength. Okay. I'm gonna write this in red. Strength, okay, is proportional to uppercase K. The extent. Okay. So it can be Ka if it is an acid, it can be a Kb if it's a base. But whatever the case, okay, higher the K value, stronger the species is. That's it. Okay. Strength is directly proportional to the K value. That's the only information we need. That's very simple. Keep this in mind. All right. So what this means is this, okay, just for clarification, okay, if it is acid strength, I just want to make sure that we understand. Acid strength is proportional to K sub A. Okay, higher the Ka value, stronger the acid. Okay, same way, base strength. You know what I'm writing here. I don't have to write this technically, but it's okay. Base strength is proportional to, what do you think? Yeah, K sub B. Okay, higher the K sub B, stronger the base is. That's it. All right, what questions, concerns, comments do we have about this? Anything? I'll reopen the question. And also, I'm going to give you another set in a bit. All right, any questions, concerns, comments about this? Anything?
Are you talking about like for the +7?
All right, let's keep this simple, okay? Higher the K value, the stronger the species is, whether it is acid or a base. That's it. All right. Now, with this, I want us to imagine what a strong acid is, okay? So when it comes to strong acids, right? Again, the acids act like, this is the way acids usually act. Okay, if this was HA, it's donate protons to water, establishing this equilibrium, right? When it comes to strong acids, this K value is greater than 1, meaning our reaction is product favored. Okay, if the Ka value is greater than 1, then it's a strong acid. Now, here's the caveat. I rarely ask you to memorize anything in my class, but I'm asking you to know this, okay? I want you to know some common strong acids, HCl, HNO3, and H2SO4. I want you to know them. There are, obviously more than this, but at least when you see HCl, HNO3, or H2SO4, I want you to know that we are talking about, or we are dealing with a strong acid. Okay. Again, what is a strong acid? Okay. The Ka value is greater than 1. If the Ka is greater than 1, it's a strong acid. Right? So there is something that we need to deal with here. It's about the wording. I'm going to actually write this here as well. Strong acids, right? Strong. Oh, no, I'll do it like this. Okay. So acid, base, okay? So we have strong acids and then we have weak acids, okay? So far what we know is if your acid is strong, then our Ka value is greater than 1. That's it. Meaning you have more products than the reactants at the equilibrium. Okay, so here's the pictorial representation for the same thing. Here's before dissociation, HA. Okay, after dissociation, you have almost no weak acid left. Everything is converted into H3O plus and A minus. Okay, and that is characteristic of a strong acid. Okay? And that's how we get a product favored reaction, OKA greater than 1. Any questions, concerns, comments? Anything? Yes. No. No. Yeah. Strong acid, when you have a Ka greater than 1. That's it. Yeah? All right. Now, I know what that question is implying something else, but I'm going to get to that. So it's implying the conjugate species of the strong acid, but we'll get to that in a second. Okay. Now, this is strong. Okay. We know strong acids. And then when it comes to weak acids, okay, what can you tell me about the Ka value? Thank you. Ka is less than 1. Can we write that too in our notes? If our acid is weak, what it means is our Ka is less than 1. By the way, it's greater than 1. If our base is weak, then Kb is less than 1. Okay, that's it. So everything is in this small diagram over here. Table. All right. Any questions, concerns, comments so far? Anything? Please. It's possible, but I haven't dealt with any of those situations. Yeah. Reese's question was, what about Ka being 1? Okay. Yeah. I mean, I haven't seen them at least. Yeah. But it's possible. Anything is possible. All right. So with that, okay. So again, when it comes to Ka is going to be less than 1 for weak acids, and then the only weak acids that you want to know, that I want you to know, is carboxylic acids. Okay, if you have this group over there, carboxylic acid group, then you are dealing with a weak acid. I want you to know that. If not, I will give you the Ka value. With that, you can determine whether it is strong or weak. Okay, and then on the other hand, when it comes to weak bases, okay, only weak base I want you to know, when you see it, you need to know them. And those are amine groups. Any compound that contains amines, that is NH2, NHR, NR2, those are called primary, secondary, and tertiary amines. We'll talk about that a little bit later. Okay. If your molecule contains a nitrogen with a lone pair, can you write that? That's much better. Okay. If your compound contains a nitrogen with a lone pair, that's the base. Hands down, that's the base. Okay. All right. What questions, concerns, comments do we have about this? Yeah, are we doing okay? Yeah. All right. So we know that. Now let's have some fun. First of all, just for completion purposes, let's do bases as well. Here are some bases. I want you to arrange them from weakest to strongest. Go ahead. All right, I'm going to close this question in 5, 4, 3, 2, and 1. All right, and here our responses is the most popular answer, and that's the correct answer as well. 90% of us are there, which is beautiful. All right, so now we know how to identify, how to distinguish between weak and strong. John. Yeah, conjugate species, we will. Yeah. Yeah, we will, well, let's say, yeah. All right. Now, another thing I want to mention is, just for completion of our notes, Okay, I'm going to write this here because Lani reminded it, right? Lani, right? Yeah. Okay. So again, the strong acids that we need to know are HCl, HNO3, and sulfuric, which is H2SO4. I want you to know them. And the weak acids that I want you to know are any compound that contains carboxylic group, COOH group. And then when it comes to bases, the only weak bases I want you to know are, like, I want you to know when you see them are amines. Okay, so any compound that contains amine, NH2, NHR, or NR2. Okay, so they have lone pair. They have a lone pair on this nitrogen. That's the characteristic of them. Those are weak bases. And when it comes to strong bases, so strong bases are metal hydroxide, especially alkali and alkaline earth metal hydroxide. Don't worry about that. So if you have a metal and then a hydroxide, okay, that's a strong base. Okay, for an example, sodium hydroxide in previous case, okay? And then sometimes sometimes if you have an alkali earth metal, then you're gonna get MOH2, okay? So these are our strong bases. Okay, I'll write an example as well. Example NaOH, KOH. Okay, those are strong bases. All right. So the idea is when they dissolve in water, they provide OH minus ions to water. That's what make them strong bases. Alison. Yes. Yes. All right. Any other questions, concerns, comments about this or anything? Okay. Now, with that, let's make sure that we know how to read or deal with pKa and stuff like that. Okay. I'm going to use this for that. Right. Here we go. Here are two compounds, naproxen and phenol. I want you to tell me which one is stronger as an acid. Hey, that's it. Okay. I think I have close to 90% answers. Actually, more than 90% answers now, I think. I'm going to close this question in 5, 4, 3, 2, and 1. All right. So, I walked around. Most of you are there already, which is good. But before I look at your answers here on top of it, I want to show you the way I think about this. Okay. So the first thing I'm going to do is I'm going to convert pKa to Ka. Okay. How do we do it? Ka. Oh, I don't like red. Okay. Ka is equal to 10 to the power of negative pKa. That's it. It's the same relationship that we use with pH. Okay. Therefore, for naproxen, the Ka value is 10 to the power of negative 4.4. Okay. And then for phenol, the Ka value is 10 to the power of negative 10. These are my Ka values. Okay. So obviously, we have a higher Ka value for naproxen. Therefore, naproxen is stronger. This is stronger. That's it. Higher the value, stronger the species is. Yeah. All right. What questions, concerns, comments do we have about this? Anything? Any questions, concerns, comments? Adeline? You're doing okay. Oh, yeah. All right. All right. So if that is the case, let's do this. Let's put them all together now. Here are 4 species. I want you to all right, we are getting close to 90% answers. All right, I think I have more than 90% answers now. I'm going to close this question in 5, 4, 3, 2, and 1. All right. And here are our responses. Most of us selected option D. Okay. Now let's see why. Now, all right, here are the decisions we need to make. Okay. The main decisions we need to make is whether these are acids or bases. All right. HCl, acid or base? It's an acid. Is it strong or weak? Yeah, it's a strong acid. So I'm going to say it's a strong acid. Right. KOH, acid or base? Strong or weak? Yeah, it's a strong base. So I'm going to say S base. Strong base. Okay. CH3COOH. This is the ingredient in vinegar, by the way. Acetic acid. Okay. Is it acid or base? Acid. Strong or weak? Yeah, it's weak. So I'm going to call it VW acid. Last one. CH3NH2. Acid or base? It's a base. Strong or weak? Yeah, it's a weak base. So I'm going to say it's a weak base. Right? This is all we need to know there, okay? So now we know if it is a strong acid, our Ka value must be greater than 1. So Ka is greater than 1, okay? So here strong base, Kb is greater than 1. And it's a weak acid, so Ka is less than 1. And then weak base, therefore Kb is less than 1. These are the K values, okay? And then we know acids donate protons to water, making H3O plus ions, meaning it increases H3O plus concentration. When H3O plus concentration increases, pH must decrease, okay? So acids increase H3O plus concentration. We know, let me write like this, okay? pH is negative log H3O plus concentration, okay? So acids increases H3O plus concentration because when it donates proton to water, okay, water becomes H3O plus. That's why H3O plus concentration increases. Therefore, pH must decrease, okay? So for acids, the pH must be less than 7, okay? For bases, it's the other way around. It decreases H3O plus concentration, therefore pH must increase. Therefore, for bases, pH must be greater than 7. Okay, pH is less than 7. pH is greater than 7 for bases. That's it. That's all we need, and that is satisfied by table D, I think, and that's why most of us selected option D. All right. What questions, concerns, comments do we have about this? Anything? Anything at all? What questions do we have? No? All right. So now I keep hearing from John about conjugate species. So that means I think I have to do something about it. Right, John? Okay, I'll do it. So let me switch to my notebook. I have a slide as well, but I prefer the notebook for this. Okay. So here's how it goes. Let's take an acid, okay, any acid. So let's call it HA. Please pay attention now. If you understand this, you will do really well on the quiz tomorrow. Okay. When acids reacts with water, it's going to produce H3O plus AQ. And what? What does it produce? Everybody, H3O plus, and what does it produce? A negative. Okay, so A minus ion. Now, here's the question for you. Say for some reason, not some reason, let's say that we want to react A minus with water. Okay. So if A negative reacts with water, right, what would happen? Will it react as an acid or a base now? It has a negative charge. Can it donate protons? No, it doesn't have a proton to be donated, right? It has a negative charge. If it has a negative charge, what can it do then? Yeah, it can accept protons. Okay. As a result of that, okay, this can accept a proton and it produces Ha and OH minus ions. Okay. So what this means is this A minus ions over here, which is produced by acid dissociation, is actually a base. Right? And that A minus ions are called conjugate base of this weak acid. Okay. So this is my acid. This is the conjugate base that is produced by that acid. So this is a conjugate pair. Okay. This is called a conjugate pair. All right. So same thing we can say about water as well, by the way. Okay. So in this case, water has accepted the proton. Okay. So anything that accepts water is called what? I'm sorry. Anything that accepts protons is called what? It's a base, right? So water in this case is our base. Okay. And then that produces H3O plus ions. Okay. H3O plus ions can act as acids or bases now. It's going to act as an acid or a base. It's going to be an acid, okay? Because if it reacts with water, it can donate that proton. Therefore, this is the conjugate acid of water. Okay, so this is my other conjugate pair. Right? And this is the idea of conjugate pairs. Okay. All right. What questions, concerns, comments do we have about this? Anything? Yeah, absolutely. Any questions, concerns, comments? Now, yes, Delia, take the microphone, Delia.
Okay, so an acid can't have a conjugate acid.
One more time?
An acid only has a conjugate base. It can't have a conjugate acid.
No.
Okay.
So acid has a conjugate base. A base has a conjugate acid.
Okay.
Yeah. Huh? Yeah. Anything? Yeah, I hear you. I hear you. Do you have a question, miss? No, not yet. Okay. Any other questions, concerns, comments about this? All right. Now, here's what's going to happen. I'm going to give you compounds. Okay. And then I want you to tell me the conjugate pairs of that when it reacts with water. Okay. Those are the questions you can get from this area. All right. Now, I want to mention one other thing here. Okay. Shoot. I'm sorry. That's bad planning from my part. Okay. Anyway, so, that is dark. That is okay, but here we go. Yeah, better. Okay. So one more time. So when acid react with water, right, you're going to get H3O plus AQ and A minus AQ. And then the equilibrium constant for this, you can write this if you want to, is equal to H3O plus concentration times A minus concentration divided by HA concentration. Okay. At the same time, my conjugate base, A minus, when A minus reacts with water, right, is going to grab a proton from water and becomes HA. It's going to become HA. And then it's going to produce OH minus ions. So it's going to act as a base, in other words. Okay. So I can write equilibrium constant expression for this. That's going to be HA concentration times OH minus concentration over A minus concentration. Because we're dealing with the base, I'm going to call this the K sub B. Okay. Now, here's the thing. Okay. Now, what I'm going to do is I'm going to multiply Ka by Kb for this conjugate pair. Okay. So if I multiply Ka by Kb, I'm going to say Ka times Kb. Okay. So Ka is H3O plus concentration times A minus concentration over HA concentration. And then if I multiply that by Kb, which is HA concentration times OH minus concentration over A minus concentration. I like this part because I get to cancel things out. HA cancels out, A minus cancels out. Okay, cancels out. And then what I'm going to be left with is H3O plus concentration times OH minus concentration. What is that? H3O plus times OH minus concentration is what? Yeah, that is Kw. This is Kw. Okay. So for conjugate pairs, what it tells us is Ka times Kb is equal to Kw. Okay, or 10 to the power of minus 14. Okay. So if I take negative log on both sides, negative log Ka times Kb and negative log Kw, I'm going to end up with negative log Ka plus negative log Kb and negative log Kw, I wrote that again. This is pKa and this is my pKb and that is equal to pKw. Okay. So in other words, pKa plus pKb is equal to 14 at 25 degrees Celsius. Okay. And this is true for conjugate pairs. Okay. For conjugate pairs, okay, pKa plus pKb is equal to 14. All right. We just derive this from, from first principles. All right. What questions, concerns, comments do we have at this point? Anything? All right, let's have some fun with this, okay? Again, I don't want you to be, it's okay if you can derive this, but I won't test you on whether you can derive this or not, okay? But we should be able to use this information. You can have this handy in your one-page note. All right. Now, let's do this. Okay. So, one more time, this is what we did. We derived this relationship. Ka times Kb is Kw. Therefore, pKa plus pKb is 14, if Toppet allows us to say it, for conjugate pairs. Right? And then we know how to identify conjugate species. For example, HCl is our acid. When it reacts, it's going to produce the conjugate base. And then H2O in this case is the base, and H3O plus is the conjugate acid as well. Okay. And then, yep, there you go. So we can do the same thing for this as well. So in this case, you will have to do this in the next question. This is my base, right? This is the conjugate acid that is produced by that base. So that's a conjugate pair. Okay. And here, this is my acid. This is donated the proton. And this is the conjugate base produced by that acid. Okay. So this is a conjugate pair. Okay. So with that, let's have some fun. Let's see. Here we go. All right. So here are some drugs that we never heard of, Adderall and Ritalin. All right. Right? Anyway, what I want you to do is I want you to tell me. Let me see. I don't know what I want to tell you. Okay, here we go. the reaction of these with water. Go ahead. First of all. So pay attention to the nitrogen of Ritalin here. Okay. So it does not have a lone pair. It has 4 bonds around it, meaning it has already used its lone pair to grab a proton, right? H plus. Therefore, that nitrogen cannot act as a base. So while you're working on your problem, I'll draw. I mean, I'll write the reaction of Ritalin with water. Okay, on my screen. So we have C14, H20, and NO.
Yeah.
2 plus.
Uh-huh.
When this reacts with water, I'm
No,
not gonna write the phases here because it's hard for me to write them.
hydrogen.
The only thing it can do is it can donate a proton by acting as an acid. As a result of that, you're going to produce C14,
It has that extra one.
H19 because you got rid of one of the protons, and NO2. Now it's neutral, right? And on the other hand, that proton was grabbed by water. Therefore, water is going to have a positive charge now, which is going to produce H3O plus,
Those electrons back.
right? So this should be the reaction between Ritalin and water. You should write the phases as well, just to get used to writing phases. And where are my conjugate pairs? So let's do that with a different color. Okay, so I'm going to use blue now. So here's my acid. Here's my acid. Okay, and then that acid produced a base, and that is this base over here. But that base is called the conjugate base. This is my conjugate base. If you want to do the same treatment with water as well, so water is acting as a base on this side, and that produces the conjugate acid. Conjugate acid on the other side. Right? So these two are conjugate pairs, and these two are conjugate pairs. John, what's up? No, he doesn't have COOH. Yeah, it doesn't have acid group because that's not COOH. Okay. Yeah. All right. I think I have close to 90% answers here. Do the same thing with Adderall as well. Okay. I'm not doing it. Adderall is the base now because it tests nitrogen with a lone pair. Right. It's going to grab a proton from water. Yeah. Oh, yeah. Brianna. Zoe, can you pass this microphone to Brianna? For that. Brianna, go ahead.
So in this, since the nitrogen doesn't have a lone pair to donate,
Ritalin?
yeah,
Yeah.
does it still act as a base?
No, it is acting as an acid, right? I wrote it as an acid.
Okay,
Okay,
That's what
only
was
thing it
throwing
can
me.
do is it can donate that proton. That's why I call this an acid. This is gonna be acting as an acid. A
okay,
weak
thank
acid,
you.
yeah? Yeah. Any other questions, concerns, comments? Brindley? All right, I'm gonna close this question now.
Because it keeps that
All right,
layer.
and then here are our responses. Some of us are still working
Right.
on Adderall. Adderall is going to grab a proton, therefore it's going to produce C9, H14, and nitrogen, and with a positive sign. That's going to be the conjugate pair of Adderall, okay, which is going to be a conjugate acid. This is the base. Adderall is the base, and when it accepts the proton, it's going to produce a conjugate acid. All right, last question for today. We're done.
Two bonds from the ring and then the H. But then once it loses that, the high it takes all the electrons from that bond and puts it back on the nitrogen, so it's back to neutral. Basically, the most simplest way to put it is you can't jump from like negative to positive like that. So if you're gonna go from positive, you have to go back to neutral. Then go
Right.
back.
Pay attention. So these guys are conjugate pairs. Right? This is the conjugate acid. Morphine and its conjugate acid is given here. Now the question is, what is the equilibrium constant value for conjugate acid reacting with water? Okay, I'll remind you because we just learned this, all right? So we know for conjugate pairs, pKa plus pKb is equal to what? pKw or 14, right? It's 14. And then pKb is given to you, which is 5.8 equals to 14. Therefore, pKa is what? Yeah, 14 minus 5.8, which is 8.2. Yeah, 8.2. Okay, if pKa is 8.2, we know Ka is 10 to the power of negative pKa. Right? So that should be 10 to the power of negative 8.2. Done. Done. That's it. I did it for you. Why did I do that? Right?